have a look at organic reaction mechanisms. So what we're going to cover, we're going to look specifically, or a bit more specifically, at alkanes and halogenoalkanes. I'll try not to be lazy and call them haloalkanes, but apologies if I do. So alkanes and halogenoalkanes and nucleophilic substitution. And then we'll look briefly at alkenes, specifically stereoisomers or stereoisomerism, and then reactions of alkenes, specifically electrophilic addition. Now, I'm not going to go through this in any more detail than just showing it to you as a scheme. Now, this is just for AS and it's not comprehensive. And if it were me, I would be adding in extra information to it as well. But if you don't have a reaction scheme or synthesis or map or whatever you want to call one of these, then I would highly recommend you make yourself one. There are lots online. There are some you can buy. There are some that are given free. So I think OCR has got a version that you can just download, which is great. You know, your teacher might have a copy that you could copy, a version that you could copy. Your friends might have already made one. So you don't have to create one from scratch, but I would recommend you create your version of one that you found, or take the time to go through the specification. We love our specification, to go through it and write down all of the different reactions that you are expected to know. Because one of the things that students find really difficult is organic synthesis. It's understanding how you start at A and you get to B. How do I get there? Or start at A, get to E. How do I get there via B, C, and D? It's a really difficult thing. It's a really difficult skill. But if you have got a visualization of it, or if you're not a visual person, if you prefer it to be written down in words, absolutely fine. Or what, you know, do whatever is going to suit you. But I would get a version of a synthesis map created, because then you can use it in exam questions when you're finding it really difficult to see the route through. And yes, if it were me, I would be adding color coordination to it. So all of the substitution reactions I might do in one color. All of the addition reactions I might do in another color. I would be highlighting when the same reagents are being used and trying to work out why. Are they being used because you're adding in the same group and it's a substitution? Are they being used because those reagents are oxidizing agents, and therefore that's why we need to use an oxidizing agent, because it's an oxidation, etc. So I would be finding ways to color coordinate it, work out when you've got the same type of reaction, oxidation, reduction, hydrolysis, condensation, etc. When you've got the same reaction mechanism, nucleophilic substitution, addition, elimination, whatever it is. When you've got the same reagents, conditions, etc., etc. So I would highly recommend you make your own, or find one on the internet and then adapt it to yourself. Things written in your own handwriting are easier to remember for your brain. So write it out in your own handwriting and then use that to remember it. Okay, so let's think about alkanes and halogenoalkanes. There's a lot of content. We're going to try and cover as much of it as we can. If you're AQA, it is this content here. If it's EdXL, if you are EdXL, sorry, it's this and this. And if you're OCR, it is this and this. So there's loads of content. We're going to try and get through as much of it as we can in as much detail as we can. Again, please do, however, use your specifications to check anything, to confirm anything you're unsure about, or how much, if you're not sure how much detail is needed, use your specification, because they are super useful. Right, alkanes. Alkanes are saturated hydrocarbons. What on earth do those two keywords mean? And what do they mean together in this context? So if something is saturated, it means what? It means it has only got single bonds. It is saturated. If it is a hydrocarbon, what's the definition of a hydrocarbon? It means it has only got carbons and hydrogens. So if an alkane is a saturated hydrocarbon, it means it contains only hydrogen and carbon atoms in only single bonds, or with only single bonds. That can specifically mean here then, because it's a saturated hydrocarbon, that there are no, that's only carbon-carbon single bonds and carbon-hydrogen single bonds. Because we know it's a hydrocarbon, those are the only elements possible, so those are the only bonds possible. Okay, so let's write that down. Let me get my pen back. Nope, not highlighted. A pen. So alkanes are saturated hydrocarbons. Oh no, I'm in a highlighter pen. They contain only carbon-carbon single bonds and carbon-hydrogen single bonds. And that is because the shortened definition of a saturated molecule is it contains only single bonds. And the shortened definition of a hydrocarbon is it's only hydrogen and carbon atoms. Therefore, saturated hydrocarbons must contain only carbon-carbon single bonds and carbon-hydrogen single bonds. Alkanes, so that is an alkane is a homogeneous series of molecules. So they have related properties, they have a trend in physical properties, they have very similar chemical properties, they differ by only CH2 per molecule in the series. They have the same general formula. What's the general formula of an alkane? I haven't written that in, so let's write that in. What's the general formula of an alkane if it's in the homologous series alkanes? It is CnH2n plus 2. So you take the number of carbons you've got, you double it and add 2, and that's the number of hydrogens you've got. CnH2n plus 2. So within the homologous series alkanes, the carbons have, well, actually, and the hydrogens, but I guess you're only spinning a single bond. Carbons and hydrogens have free rotating sigma bonds. What is a sigma bond? What is a sigma bond? How do we define or describe a sigma bond? It is the end-to-end overlap or end-on-end overlap of orbitals. Or you can talk about the orbitals pointing, the overlap of orbitals happening as the orbitals are pointing towards each other, but I prefer end-to-end overlap of orbitals. Overlap of bonding orbitals, or just orbitals. So yeah, you can talk about orbitals pointing directly at each other if you want. And because alkanes contain only single bonds, that means the shape around a carbon is what? The shape around each carbon is tetrahedral. Because each carbon makes 4 bonds, tetra meaning 4, like Tetris, the game, each block is made up of 4 smaller blocks, so tetra meaning 4. So around the carbon it is tetrahedral, which means what is the bond angle? This is the only bond angle I personally have ever memorized, because everything else you can work it out if you know a little bit more detail. This is the only bond angle I've ever memorized because it's a weird one, and I can't do the maths to work it out on the day. So bond angle is 109.5, because if you take a sphere and divide it into 4, the angle between these 4 points is 109.5 degrees. That maths is way above me, but that is our bond angle. So if, for example, we draw it out in our lovely 3D diagram, so wedge and dot, let's point that down a little bit more, make it a little bit better looking. Then we've got our tetrahedral shape. And if we just show those end-to-end orbital overlaps, if you've got your carbon and hydrogen, let's do it in a different color actually, then a carbon orbital is this sort of shape. Don't worry too much about orbital shapes. If you haven't done bonding orbital shapes, then don't worry too much. But they look a bit like that. And let's make the hydrogen's orbital red. So they are pointing, whoops, there's end-to-end overlap, as in they are pointing at each other. And that means you can get full rotation. So that carbon can rotate as much as it likes. The hydrogen can rotate as much as it likes, because the orbital, just like a ball and socket joint, the orbital stays interacting. The orbitals stay interacting. Because this is the shape of the orbital formed, and it can rotate without breaking the bond. Let me just get rid of that if I can. Okay. What else do I want to say? Nothing, I don't think. Okay. So it's important to remember that alkanes can freely rotate, and they've got a tetrahedral shape around the carbon, 109.5 degree bond angle. We're going to compare them to alkenes later. Alkanes have a low reactivity with many reagents. Why? Just have a quick think. Why are alkanes going to have a low reactivity with many reagents? Why is the end product of a reaction usually an alkane, and then we don't go any further? It's for a multitude of reasons. I'm just going to take a drink. Try not to make a mess. This is because carbon, hydrogen, and carbon bonds have high bond enthalpies. If they've got high bond enthalpies, it means what? It means they require a lot of energy to break. I'm going to say E for energy. And also because carbon-hydrogen bonds have low polarity. So as well as it taking a lot of energy to break those bonds, carbon-hydrogen bonds, sigma bonds, have low polarity. That is because carbon and hydrogen have very similar electronegativities. Because of that, any ending product isn't going to be stabilized by something attacking it because the carbon-hydrogen bond is not polarized already. You don't have to be able to explain that. I'm just trying to explain it to you guys. So because it's got a low polarity and because it's got high bond enthalpy, alkanes don't tend to be very reactive. They do, however, undergo combustion readily. Combustion is an exothermic process. Exothermic, let's try and spell that right. Excuse me, exothermic reactive. So lots of energy is released, which means we have quite stable products. That's what drives the reaction. That's why it happens readily, or one of the reasons why the reaction happens readily. But it's a rapid oxidation reaction with oxygen, and that's why alkanes are often used as fuels. What's the definition of a fuel? Definition of fuel is something that we can burn or that we can combust that releases a lot of energy. You can burn lots of things. It doesn't mean that we're going to use them as a fuel because they don't release enough energy per, mass of substance. So alkanes, however, do release lots, so we're going to use them as fuels. Let's have a quick go at this question. I'll give you half a minute just to come up with this. Not even half a minute. Let's go 10 seconds. Context here. Alkanes is my context. I'm stating, that's my, what's it called? Command word is state. So small answer. And the direction, specifically 8 hydrogen atoms, molecular formula and name of something with 8 hydrogen atoms. What would you put? Well, if we can remember, it's an alkane. Alkane means the general formula is CnH2n plus 2. I've got 8 hydrogen atoms, so 2n plus 2 will equal 8. That means n is 3. So my alkane must be C3H8, which is propane. Hopefully everybody is happy with that. Let's think about halogenoalkanes. This is usually one of the first mechanisms that you're introduced to in A-level, and mechanisms can feel a little bit scary. Actually, hopefully, when you go back and look at your free radical substitution mechanism, which is what we're going to look at now, you realise actually they're not that scary. If you do find it scary, I would highly encourage you to spend a little bit more time actually thinking about the mechanism that happens here. So you don't have to be able to do the mechanism. You don't need curly arrows, but I probably will do a couple of curly arrows to help with understanding. You do have to do a curly arrow, to show homolytic fission, which we'll come to in a minute, but you don't have to do what we're going to call a proper mechanism here. But if you do find it hard to understand and get your head around free radical substitution, I would highly recommend you actually think about the actual mechanism, because it makes it a lot easier to fit the puzzle pieces together. But we're not going to think about it too much now, unfortunately, because we don't have time. So let's just think about what we need to know. What do we need to know? We have to know that there are 3 steps in free radical substitution. The first step happens when there is the presence of UV light. So if we have a halogen or molecular halogen and the presence of UV light or a high temperature, then we can undergo free radical substitution, because the first step can happen. And that first step is called initiation. It's the formation of a radical. What is a radical? A radical is a species with an unpaired electron. Why is that important? It's a stable species with an unpaired electron, I should say. Stable, because it can exist. Not stable because it's unreactive. It's not unreactive. They're very reactive. Radicals are very reactive. They are also, just as a common issue, they are also neutral. So a common thing that we think about when we draw, for example, a chlorine radical, is you think, well, because it's got an electron that's on its own, it must have a negative charge. It doesn't. They're neutral, because a chlorine atom with an unpaired electron, because it's got 7 electrons in its outer shell, so one of them is unpaired, has got, how many has chlorine got? 17 electrons, 17 protons. So it's a neutral species. A chlorine atom is neutral. We just rarely see radicals because you have to have that extra energy present in order for them to exist as their very reactive, unstable radical in their radical form. Otherwise, chlorine would be bonded. It would be an ion, so it would have gained an electron to make it stable, or it would be bonded in a covalent bond, so it would also be more stable because it's sharing that extra electron. Radicals exist because we've given those species a little bit of extra energy so they can exist in their high energy unstable states. But that doesn't mean that they've got an extra charge. It's the same thing. It's an atom, but that is allowed to exist with an unpaired electron. So initiation happens when we form a radical. We'll look at this. We're looking at an example of initiation in a minute. But one of the ways that I kind of help students to remember the difference between initiation, propagation, and termination is, what does an initiation step have to look like? It has to start with what I'm going to call a normal species. So a bonded molecule, compound, whatever it is. It has to start with a normal species and form 2 radical species. If it does that, it's initiation. It's creating at least 1 radical. You can't start with no radicals and not create 2 because of the way that homolytic fission happens. But we have to form a radical in initiation from no radical. The next step is propagation. Propagation is continuing radical formation. So it's taking a radical, reacting it with something to create a radical and something else. So propagation steps must start with a normal species and a radical species and create a normal species and a radical species. If somehow your propagation step has combined 2 radicals to make a normal species, that's not propagation. If somehow your propagation step hasn't created another radical, it's not propagation. The word propagation means continue. So we have to continue with our radical species. You must create another radical species out of your propagation step. Make sure that your radical is regenerated. And then also a termination step or termination steps. This is where we start with 2 radicals and we create a normal species. 2 radicals collide to form a stable product. The stable product must have no unpaired electrons. So no radicals in the product of a termination step. Again, it's terminating, it's finishing this free radical substitution mechanism. So we've got to get rid of all the radicals. Technically, radical substitution can continue until all of the hydrogen atoms in an alkane have been replaced. So substitution, we're substituting the hydrogens in an alkane for halogens. That's how our free radical substitution, that's what the substitution does. So technically, it can happen until all of the hydrogens are replaced. Usually, though, we only look at the mechanism for the replacing or the substitution of a single hydrogen. But be careful, because they can ask you to replace or substitute the second hydrogen or the third hydrogen or even the fourth hydrogen. So be aware that you could be expected to do all of them. We're only going to look in detail at one, replacing the first one. This can only happen if conditions are maintained. So if you've got your enough of your radical species, and if you've kept the light, UV light and or high temperature present. So if conditions are maintained, i.e. UV light or our high temperature, so usually around 300 degrees C. Radical substitution is also unpredictable. And again, one of the things we're not going to focus on too much, but that you do need to be aware of, is that you can create a mixture of products. We've called them side products here, but actually they're just products, because we can talk about what we would class as our usual initiation, propagation, and termination steps. But what if those species don't end up reacting? What if you get to other radicals reacting? You might create a product in a termination step, which is not what you were expecting or not what you were going for. So we can create lots of side products in our radical substitution reaction. So let's think about some reactions. We'll go through it nice and speedily, just so that we don't spend too much time on this. But we've got initiation step, propagation step, and termination step. Let's work. I'm just going to go as basic as possible. But bear in mind, obviously, you might be expected to do things that are a little bit more complicated. Not too much more complicated, thank goodness, but a little bit more. So initiation, let's start with our chlorine. So I'm going to do chlorine, the substitution, free radical substitution of chlorine with methane. So we've got Cl2 and we've got our UV light. What is going to happen? What is going to happen? We'll think about the mechanism in a little bit more detail on the next slide. But what is going to happen? We're going to get the formation. It's an initiation step, so we've got to form a radical. In this case, we have to form two radicals because we're undergoing homolytic fission, so we must form two radicals. Now, you will always be expected, no, let me rephrase that. There are always two propagation steps to get to the product that you're aiming for. There's always two. You might only be asked to give one, or you might be asked to give the second propagation step or the first propagation step or something like that. But there are two. There are always two. The first step in the propagation steps is preparing your radical for the second step, which produces the product that you're aiming for. And I'm using quotations because you might be asked to be writing the propagation steps to form an unwanted side product or something. So the thing that you're aiming for is produced in the second step. So the first propagation step starts with your alkane. And I'm going to draw it like this to try and make it a little bit easier to see. But this is methane. So I've just drawn in one of the hydrogen carbon bonds, just to kind of highlight that that's what's going to be broken. That's my normal species. So I also must have it reacting with a radical. That's my normal species. You're then going to form, or you're going to break this carbon hydrogen bond using homolytic fission. So they're going to separate. You're going to take one electron each, and that means we're going to end up with a methane radical, and sorry, that's a rubbish dot, a methane radical and HCl, because the chlorine radical is reacting or stealing away the hydrogen and its electron to form a covalent bond and leaving your methane radical or CH3 radical. So we've prepared our radical. Notice we've got a normal species and a radical going to make a normal species and a radical. I'll also just make a quick note. It doesn't matter massively where you put your radical dot. If it is a radical, you must put your dot because you need to tell other chemists that you know that that species has not made all of its bonds or has not reacted to form an ion. and that is on purpose. So we must make sure we draw the dot that represents it as a radical. That is our unpaired electron on its own. But it doesn't matter where you put it. You could put it, so for example, I could put my chlorine radical on the left-hand side, or I could put it on the right-hand side. Just if I were you, I'd try to be consistent between elements so that your examiner isn't confused. And personally, I find it easier to understand and remember if I draw the dot next to the species that is carrying the radical. Not always easy to do, but that's what helps me to think through the process and to think about the mechanism. But it doesn't matter if some are on the right and some are on the left, as long as you try and keep the radical as close to the species that's carrying it, then that's fine. And you haven't drawn two or on one species or anything like that. Okay, second propagation step takes the radical that we've just prepared and we're aiming for a product. But what do we react with? What is there lots of hanging around that is able to be reacted with and that is going to help us produce a radical that can propagate afterwards? Well, it's got to be something that can help us produce another chlorine radical. So it's got to be a Cl2. And there's lots of it around. We know there is because we started with it to begin with. That means we're going to end up forming a chlorine carbon bond. And because we've broken the chlorine-chlorine bond, we end up with a chlorine radical. Again, we started with a radical in a normal species and we ended with a radical in a normal species. We have propagated the free radical substitution. And finally, termination. Now, there's normally, when you're asked to give a termination step, have a look at the specifics. Often they will specify which termination step they want you to give. So just be careful. I'm going to give all three that are currently possible within our setup. But of course, if you've got side product, if you've got further substitutions happening, there could be loads of different propagation and termination steps that you could be asked to give. So just read the question really carefully and check what it is they're expecting from you to make sure that you give them the answer that they want. But there could be, in this case, 3 different termination steps. How can we get 3 different ones? Well, there's termination step, which is just the reverse of initiation. So that's kind of the easiest for me anyway to remember. It's just the reverse of initiation. 2 chlorine radicals forming a normal species, that's termination. 2 radicals form a normal species. But what if we look, we've actually got a CH3 radical floating around as well. Now, the chances of these radicals colliding is very low, which is why free radical substitution is such a horrible reaction, because the chance of a termination step happening is very low. But it is still possible that, for example, 2 chlorine radicals will collide. It's also possible that 2 of our methane radicals would collide. So what would we form then? We'd form a C2H6 molecule, where you could write it as CH3CH3 if you wanted to. But you will have formed ethane if those 2 collide. Or maybe, again, it's going to be very unlikely to happen, but it is still possible. So it could be one of the products, could cause one of the products. What happens if your methane radical combines with your chlorine radical? Well, then look, we make our product that we wanted again, or that we were aiming for above. So all of it is very unlikely that they will happen. It's unlikely that termination steps actually happen at all, because the likelihood of 2 chlorine radicals combining is very low, or 2 radicals, meeting is very low, because they're not going to be very concentrated, but it is possible. So those are 3 possible termination steps here. Okay, let's whiz on. So you don't need to know the curly arrow mechanisms for initiation, propagation, and termination. Sorry, for propagation and termination, but you do need to know it for the initiation step, because we need to talk about fission, specifically homolytic fission. So if your covalent bond fission is the breaking of a covalent bond, we can have homolytic fission or heterolytic fission. Homolytic fission is when both atoms in the bond receive 1 electron from the bond pair, and homo meaning same, same splitting. So lytic or lysis is splitting. So homolytic means splitting similarly. So both species receive an electron. We create 2 species that are the same type of species, so 2 radicals. For example, let's have a look at, let's do it with chlorine because that's one of the most common ones. In the presence of UV light, we create our two chlorine radicals. So how does that happen? There are two electrons in the chlorine-chlorine bond. Each chlorine has obviously got 3 lone pairs as well, but the shared pair of electrons involved in that bond is shared between the two chlorines, and one electron goes back to one chlorine, the other electron goes back to the other, and that's why I've kind of drawn a half-headed arrow. And it's a point of contention for me because lots of people call that a single-headed arrow. Lots of people call it half-headed arrow, or, you know, half an arrow or whatever. And so it's confusion between double-headed arrows which point in both directions, or a double-headed arrow that's got both its bits to it. It's a confusion. Just be sure you know what I'm going to call single-headed arrow looks like. Okay, it's only got a single side to it, and that's representing the movement of one electron. A double-headed arrow, or an arrow with both bits to the point, is representing the movement of 2 electrons. So specifically, it's the movement of 1 electron. That's with homolytic fission. With heterolytic fission, one atom in the bond receives both electrons from the bond pair. And this is what we're used to when we talk about bond fission, when we talk about breaking covalent bonds, because usually we're looking at the resulting formation of an ion. So if we've got, let's just do a halogenoalkane. Heterolytic fission often comes from when we've got a polar bond, because we've already got partial splitting of that bond. The electrons are already spending most of their time around one of the species, in this case the bromine, the more electronegative species. And so both electrons, the pair of electrons, will end up moving over to the bromine. That means we end up with a species with the opposite charge. We've got a CH3 plus and a Br minus. So hetero meaning opposite or different, charged species at the end. You do need to be able to show what they're called, arrows, curly arrows for heterolytic and homolytic fission, with an example that you would be given in the exam. The reverse of either, hopefully we're clear, is called covalent bond formation. So either with 1 electron coming from each, or 2 electrons coming from somewhere, doesn't matter. In both cases, we are forming a covalent bond. So that's the reverse process. Okay, let's have a quick go at this one. I'm not going to give you too much time to do it because I'm very aware that I could easily run out of time going through all of this stuff. But bromine and ethane are heated together under UV light to produce C2H5Br. Name the reaction mechanism and state 3 examples of unwanted side products that may be produced. We're assuming here that unwanted side products is not what we would consider to be the main product. Or if this was free radical substitution to produce a halogenoalkane, that singly substituted halogenoalkane is the wanted side product. So anything else would be unwanted. Suggest how these products may be separated or could be separated. So, context. Looking at what I've got an alkene. So I've got an alkane and a halogen. So my context is reactions between alkanes and halogens under UV light. Now that's the nice little flag for me, because that is the thing that makes me go, oh, free radical substitution, UV light. So that's my context. The command word is name. So I need to give a name of the reaction mechanism. So short answer, and then a state. I need to state, so again, short answers, 3 examples of side products. But then I also need to suggest how these products might be separated. So I also need to give an example of how they might be separated. Again, this is a suggest question because this is not specific recall knowledge that I've been given in my exam, in my specification. I haven't been told specifically to know how to separate unwanted side products in this specific reaction. Therefore, I can take comfort in the fact that this isn't something I should be able to recall. It's something I should be able to work out. So name and then suggest. And state as well, really. And then direction, consider unwanted side products and separation. So I've been directed to think about the unwanted side products and then how I can separate those. So what would you say if this was you? Bromine and ethane are heated together under UV light to produce C2H5Br. So that's our wanted product. Name the reaction mechanism. Well, UV light, my head says free radical substitution. So that's my free radical substitution. Just check my spelling. That's my reaction mechanism. Give 3 examples of unwanted products that might be produced. Well, I'm undergoing substitution from C2H5 Br. So from C2H6 to C2H5Br. So what else could happen? What other products could be produced? If they'd specified in the termination step, that might have given me a little bit more guidance, because the termination step involves radicals. So that's what I'm going to use, because that is very easy for me, therefore, to see side products. So what the radicals that are going to be present? The radicals that are going to be present are bromine radicals. So if 2 of those were to combine, we would end up with Br2. That's unwanted because we're trying to produce C2H5Br. So Br2 is going to be unwanted. What's the alkane radical that's going to form? Well, if it's coming from C2, it's coming from ethane, so C2H6, it will be C2H5 radical once we've removed one of the hydrogens. So if I have 2 of those, that's going to produce an unwanted side product that's C4H10. Or you could write the full, what's it called? The structural formula for it as well, if you wanted. So C4H10, that's another unwanted side product. Or what else? Technically, you could have a further substitution. So something, so Br2, C4H10, those are my 2 unwanted side products. I've given the equations to kind of help us understand it. They haven't asked for it. So they've just asked for the unwanted products. So that's that one and that one. And then what about if I had a double substitution, C2H4Br2? That's also an unwanted side product that could be formed. There are quite a few answers you could have given here. That's just an example of some of them. How would I separate these? Well, how can you separate species that have that are all similar but not the same? What examples of separation techniques do we know that would work here? So there's a couple you could give. You could talk about chromatography. If you've learned about chromatography already, then you can separate via column chromatography or gas chromatography. These are probably gases, so gas chromatography. If some of these are liquids, so bromine would be a liquid, it'd be easy to turn it to a gas, but it is a liquid, so you could also use fractional distillation to distill off some of these. Again, actually, butane's still a gas, isn't it? Yeah. So if we cooled it down enough, we could use fractional distillation. That would work, or a separating funnel as well. If you've got liquids, you could use a separating funnel. That would be a liquid. I'm pretty sure butane is a liquid. So butane is still a gas. So again, we'd have to cool it, but we could cool it down and then use a separating funnel. That would be fine. Okay, how are we doing for time? Fine, let's keep going. So that's 5 marks, 1 for the mechanism, 1 each for an unwanted side product, and 1 for your separation technique. Nucleophilic substitution. Let's have a think about another mechanism. Specifically useful when talking about, or used, sorry, when talking about halogens. You need to know the definition of a nucleophile. The definition of a nucleophile is an electron pair donor. You can work out what a nucleophile is if you aren't confident on the definition, because nucleo, the nucleus of an atom, is positively charged. Phile means likes. So a nucleophile is a species that likes positive charge, is attracted to a positive charge. So a nucleophile, sorry, is going to be attracted to an area of positive charge and able to donate a pair of electrons to that positive charge, or willing to donate a pair of electrons to that positive charge. So a nucleophile is an electron pair donor. It's kind of my thought process in it. Nucleophiles can attack a partial positive charge or a fully positive charge, actually, if needs be, resulting in substitution occurring. Let's think about an example mechanism. We've kind of already thought about it, or we've at least thought about the beginning of it, but let's just make it simple as possible. Okay, so one of the things that I try and do, and we haven't got a huge amount of time, so I can't spend ages doing it, but if we had all the time in the world, then we would. But one of the things I try and encourage students to do when thinking about mechanisms, rather than just learning the mechanisms rote and just recalling them exactly as you have learnt them, trying to understand them. If you can understand them, then if you're given an application of knowledge question in your exam, you're not stumped. If you can understand how species interact in a mechanism, then you can apply that theory to any new situation. If all you've done is memorized how you get from A plus B to C and D or whatever, then if you're not given A and B, then we might have a minor panic attack in the exam. So I would 100% recommend you think about how are these species going to interact. Here we have got halogenoalkane. So what's interesting about that halogenoalkane? The interesting thing that's going on is that the halogen is much more electronegative than the carbon. That creates a polar bond. That polar bond is attractive, or the positively charged carbon, sorry, the delta positive carbon, I should say, is attractive to a nucleophile. And I'm going to call my nucleophile NuC. And I'm going to give it a full positive charge. Not all nucleophiles do have full negative charge. Not all nucleophiles do have a full negative charge because ammonia, NH3, can act as a nucleophile and it doesn't have a full negative charge. But in this case, just for simplicity, I'm going to use an example with a nucleophile that has a full negative charge, like hydroxide, for example. That lone pair of electrons, how is that going to interact, that negatively charged nucleophile, or that lone pair of electrons, how's that going to interact with my halogenoalkane? Well, electrons are negative. They are attracted to positive things. They are repelled by negative things. That's just our basics of attraction and repulsion with positives and negatives. So these electrons are going to be attracted to, oops, why is that not drawing? Let's try again. Oh, I've got a funny dot now, never mind. Oh no, why is this not working? I wonder if my pen battery has run out. Just going to give it a second to see if it can recharge, but it has just been recharging. It shouldn't be, it shouldn't have run out because it was charging all through lunch. There we go. Maybe it was just having a funny five. Okay, there we go. We're back, sorry. So the lone pair on the nucleophile is going to be attracted to that partial positive charge. That's where that's the direction in which the electrons are going to move. They're going to move towards the thing they're attracted to. That carbon can't have 5 bonds. It's got a pair of electrons that are being attracted to it, so it would form 5 bonds if something else didn't happen. So in this case, that pair of electrons in the bond is going to move away and towards our halogen. That means we end up with our species, which has now got the nucleophile on instead. And in this case, it's X minus. Let's just double check we have done a balanced equation. We have got an overall, we've got the same number of atoms on each side of the equation. So it's tick, we've got conservation of mass. And we've got an overall negative charge on the left-hand side of the equation and an overall negative charge on the right-hand side of the equation. So I haven't lost or gained any random electrons. Yay, I've got conservation of charge as well. Oops, I might have slightly written on my next bit, never mind. So that is an example of nucleophilic substitution, specifically SN SN2. If you are an exam board that covers SN1 and SN2, we're not going to look at it specifically today because it isn't all exam boards. But have a think about how you know it's SN2 and what SN1 would look like if it was different and why. So reactivity of a halogenoalkane here is determined by, as always, a dominant factor, but there are contributing things or there are conflicting things. So dominant factor. There are two things that can contribute. The strength of the carbon-halogen bond can contribute to how reactive a halogenoalkane is, and the polarity of the carbon-halogen bond. The more polar a bond is, the more reactive it's likely to be, usually. That's why halogenoalkanes are more reactive than alkanes, for example, because alkanes don't have polar bonds, halogenoalkanes do. But also the strength of the carbon-halogen bond is going to play an impact. It's going to have an impact as well. The stronger a carbon-halogen bond is, the more energy is required to break, and therefore the less reactive it is. Let's just pop that down. So stronger carbon-halogen bond requires more energy, which is going to make the halogenoalkane less reactive. And polarity of the carbon-halogen bond, the greater the, let's just jump straight to it. The greater the polarity, no, that doesn't make sense. The greater the dipole, that's better. The greater the dipole, so the bigger the electronegativity difference, and therefore the greater the dipole, for the nucleophile to attack, the more reactive it's going to be. So we have got two conflicting factors. What is the dominant factor then? The dominant factor is the strength of the carbon-halogen bond. Both play a part, the same as we were talking about with our trends in periodic table, they both play a part, but the dominant factor is the strength of the carbon-halogen bond. So we'll link this to hydrolysis in a second because that comes up in your specifications. But both are interesting to talk about and think about, but the dominating factor, or the thing that determines how reactive a halogenoalkane is the strength of the carbon-halogen bond. So what do we need to know about the strength of carbon-halogen bonds then? Let's apply it to hydrolysis. Hydrolysis is any reaction where a reactant is broken down by water. For halogenoalkanes, hydrolysis is a nucleophilic substitution reaction. We are swapping or substituting our halogen for OH from the water. For example, let's give a specific example. I'm not going to make it too specific, sorry. Let's just do that. So our nucleophile in this case is our OH minus. How are these species going to interact? I don't need to have memorized an exact mechanism. I can apply it here. What's interesting about these species? Well, I've got a lone pair on my nucleophile, and I've got a very polar bond. So how are those going to interact? Well, we're going to get the lone pair being attracted to the delta positive carbon, and that's going to force the iodine off. Again, I'm showing this as an SN2 reaction for those of you that do it. And then we're going to form our alcohol and our iodide species. Again, I can double check. I've got conservation of mass and conservation of charge, so I haven't missed off any charges. I haven't forgotten anything. Why is hydrolysis interesting to us, or why are we looking at it specifically here? We're looking at it because one of the practicals that you might have done or might be doing and might be asked about is the rate of hydrolysis of halogenoalkanes. We can look at the rate of hydrolysis, sorry, we can look at the rate of hydrolysis to prove or to determine halogen bond strength, halogen carbon bond strength, carbon halogen bond strength. because the faster the hydrolysis will happen, the weaker that carbon-halogen bond must be. So, which is weakest, which is strongest, which is therefore going to be the fastest rate of hydrolysis, which is going to be the slowest rate of hydrolysis. Slowest hydrolysis to fastest hydrolysis for our carbon halogens, specifically chlorine, bromine, and iodine. But I guess we could talk about fluorine as well if we wanted to. The slowest hydrolysis is going to happen with the strongest carbon halogen bond. Because the stronger that bond is, the more energy is required. So the less likely it is that the species are going to collide with enough energy for the reaction to happen. And so the longer it's going to take for that hydrolysis to occur. And the faster the hydrolysis is, that must mean that there is that happens with the weakest carbon halogen bond. It's easier to break, requires less energy to break, so it can happen faster. So which carbon halogen bonds are stronger, which are weaker? We've said the strongest is the top of the group. Carbon fluorine bonds are stronger. So that's the strongest. Then it goes down the group in a nice little trend. Make sure I get them in the right order. Let's do it in a different color. So as you go from the slowest hydrolysis to the fastest hydrolysis, as you go down the group, we get a weaker carbon halogen bond strength. Which increases the rate of hydrolysis, or allows the rate of hydrolysis to increase. Try to spell hydrolysis correct. Hydrolysis to increase. Just really quickly, why is that bond strength? Why do we have that difference in bond strength? It's to do with the overlap of orbitals. Carbon and fluorine are very similar in size, so their orbital overlap is going to be great. It's going to be really big because they're very similar in size. They can get very close together, so you can have a short bond and a strong bond. Carbon iodine's huge compared to carbon. That means their orbital overlap is going to be really far apart, so really the bond is going to be longer because iodine's so big. So its orbital overlap is going to be weaker, it's going to be rubbish, and therefore it's going to be further apart and a weaker bond. So it's to do with orbital overlap, but specifically bond strength determines rate of reaction and therefore rate of hydrolysis. Okay, let's keep going. How are we doing for time? Let's just do this really quickly, I think. So, give the product of the following reaction and what reagents could be used to reform the halogenoalkane. It's good thing to recognize. Here we've got our halogenoalkane and aqueous sodium hydroxide. Those of you that have covered it already will notice if it's ethanolic sodium hydroxide, you actually end up with an elimination reaction happening. But in this case, as it's aqueous, we get nucleophilic substitution. So I can recognize it as nucleophilic substitution. So I'm going to be swapping out the halogen for my nucleophile, which is going to be OH minus. So I'm going to end up with how many carbons? 1, 2, 3, 4 carbons. And the OH. It hasn't asked me for a displayed formula. It's just asked to give the products. So if I didn't do a displayed formula, it wouldn't be the end of the world. I could, if I wanted to, technically give a structural formula, or even a molecular formula, because they haven't asked for anything specific. In an exam, they probably would ask for something specific, so just make sure you're doing what you've been told. Or, just as a little aside, actually, if you give more detail than they're asking for, you can still get the mark, as long as it's not incorrect. So if they ask for a structural formula and you give the displayed formula, you can still get the mark because displayed formula gives the structure and it gives the connectivity via bonds. So if you're unsure or you think it will help you to work out what a product is, you can absolutely give more detail than you've been asked. The issue comes if you've been asked to give a displayed formula and you give a structural formula, for example, you're removing some of the detail that you're giving your examiner, and so you won't get the mark. Or if you've been asked to give a displayed formula, a structural formula, and you give a skeletal formula, you're taking away some of the detail because you haven't put in the carbon, the hydrogens and stuff. So again, you probably wouldn't get the mark. So you can give more detail than you've been asked for, but don't give less. Back to the question then, sorry. I should probably have, so it's a nice little check that I just did then and realized I haven't finished the question because conservation of mass, I haven't included anything else on the right-hand side of my equation. So my equation's not finished. Well done if you noticed that before I went off on my tangent. But quick check, conservation of mass, I haven't finished because I haven't included my NaCl, which is the other product that would be produced. That equation was not correct and not finished, so I wouldn't have got the mark for it until I put in that other product. If you've only been given OH minus and you haven't been given the sodium, or if you only include OH minus on the left-hand side, you only need to give Cl minus on the right-hand side. But because I've been given sodium, I'm going to include sodium on the right-hand side. So I do have conservation of mass and I have conservation of charge. Next question, what reagents could be used to reform the halogenoalkane? How do you go from an alcohol to a halogenoalkane? Well, I'm going to need a Cl minus ion and an acid catalyst. So HCl would work perfectly, or any appropriate acid catalyst and a Cl minus catalyst and the Cl minus ion, so a chloride salt, an appropriate chloride salt. I would just remember HCl if I were you, it's easier. Okay, I'm going to skip forwards to think about alkenes. Oops, sorry, there we go. Alkenes. I love a bit of alkene chemistry because it really gets into the nitty-gritty of chemistry. If you're an AQA student, these are the sections we're going to be talking about or looking at. If you are Edexcel, it is these. And if you're OCR, it is these. I'm just going to take a drink. So let's see if we can speed through this. Alkenes are unsaturated hydrocarbons containing a carbon-carbon double bond. Again, this word unsaturated means that it contains at least one double or triple bond. Oh, I've just put my pen away, whoops. And the hydrocarbon bit means it contains only carbons and hydrogens. What's the general formula of an alkene? The general formula is CnH2n. Because you've got the double bond, you haven't got those extra two hydrogens that you do on an alkane. So alkenes are unsaturated hydrocarbons containing a carbon-carbon double bond. At least one carbon-carbon double bond. Could be more than one, technically. But if we're talking about the homologous series of alkenes, we're only going to be talking about one carbon-carbon double bond. How do alkenes differ from alkanes? Well, alkenes have both sigma and pi bonds within them. Sigma and pi. What on earth are they? So the sigma bond, that's what we often consider to be the single bit of a bond because it's the end-to-end overlap like we looked at with our alkanes. But pi bonds differ because they are sideways overlap of orbitals. So unlike a ball and socket joint, which is kind of pointing at one another, and it means that we get that free rotation, pi bonds are sideways overlap, and it's not really easy for me to do it because my hands aren't 2D enough really, but you can hopefully see it with these 3D kind of balloon-like models. When you've got orbitals that are sat next to each other, kind of parallel to one another, you can get sideways overlap. The trouble with that sideways overlap is that as soon as you get rotation, my bond is broken. As soon as a carbon rotates, my bond breaks because they're no longer pointing at one another. The orbitals are no longer pointing at one another. So that's one of the troubles? Yeah. One of the issues which we'll come to in a second. We have no rotation allowed with our sideways overlap. Let's add that in. Sideways overlap of orbitals. What's the shape around a carbon, or around the alkene carbon in an alkene? What's the shape? We've only got 3 areas of bonding, areas of electron density. So that means we have got 120-degree bond angles. The shape around it is trigonal planar. Trigonal planar because 3, trigonal, tri, trigonal planar, planar because they're flat, they're within the same plane. So planar molecules, and they are 120-degree bond angles. How do we know it's 120? Because all the way around would be 360, and it's divided by 3 gives 120. Because I know it's trigonal planar, 3 areas, and they're flat, trigonal planar, I know that it's 360 all the way around, so I divide it by 3 to get 120. I don't memorize that trigonal planar equals 120 degrees. I work it out every time. Obviously, feel free to memorize it. I'm just helping you to, where possible, not have to memorize everything. If we can work it out, it hopefully will make it easier. Okay, so we've mentioned this lack of rotation. What does that cause? The lack of rotation causes the structure of alkenes to be a little bit more interesting in some cases than alkanes, because they have pi bonds, these sideways overlap of orbitals that prevent rotation about the carbon double bond. It means when you've got a molecule with a carbon-carbon double bond in it, the position of the groups on those carbons has an effect on the structure. It means we can form what are called stereoisomers. Now, because if you did get rotation, if you wanted to rotate that carbon, you'd break the carbon-carbon double bond. Breaking a bond, we know, requires energy. So you're never going to get free rotation around a carbon-carbon double bond, because you'd have to provide energy for that to happen in order to break that bond. So you're not going to get free rotation around. You can force it to rotate, but then you just break the carbon bond. So all you're doing actually there is a reaction. You're not just rotating. So stereoisomers. There are 2 different ways you can name stereoisomers. Not every exam board has to know both, and for some reason we've not written it down. So just double check in your exam board whether you mention both types. You'll see it all over the internet and all over revision guides and websites, etc. So it's a good idea to get to know both and understand that there is a difference between the 2. But not all exam boards have to know both, and I can't remember which ones don't. So just double check. But there's EZ nomenclature and cis-trans nomenclature. EZ nomenclature is kind of the cover-all way of describing stereoisomers, because you can use it for whatever groups you've got on your carbons, either side of a carbon-carbon double bond. What we're looking at is the position of, I'm going to call them priority groups or higher priority groups, either side of a carbon-carbon double bond. So on each carbon of a carbon-carbon double bond. In this molecule, my higher priority groups, which we measure by looking at the highest atomic mass going out from the bond. So carbon is higher atomic mass than hydrogen, so my top group has priority. On the left-hand side, the carbon in the bottom group has priority over the hydrogen, so my bottom group has priority. That means the highest priority groups are on opposite sides of the bond, of the carbon-carbon double bond. One is up, one is down. They are opposites. For Z, or for an example for Z, this is when our higher priority groups are on the same side. Here, my higher, let's do actually, sorry, I'm just going to make it a little bit better. Apologies, I should have done a non-same group just to make it a bit clearer. So I'm going to put chlorine down there in the bottom left-hand corner, and I'm going to do the same for this molecule as well. It's still higher priority than hydrogen though. So on my right-hand molecule here, on the left-hand carbon, chlorine is the higher priority because it's got higher atomic mass than hydrogen. On the right-hand one, carbon has a higher atomic mass than hydrogen, so my higher priority group again is on the bottom. That means on this molecule, the higher priority groups are on the same side of the carbon. They're both below the carbon bond, carbon double bond. So they are on the same side. We call these Z isomers. So E is opposite, Z is the same. It comes from the German, which if I tried to pronounce, I'd probably butch. So I won't have a go. But it comes from the German, the E and the Z. The way I remember it, it's silly, but it works for me, is Z is on the same side. That's how I've always remembered it. That's how I will continue to remember it forever. Z is on the same side. So they're both below the carbon-carbon double bond. So they are on the same side of the double bond. Same side of the double bond. So they are on the same side, they are Z. If you, however, have got molecules where you've got two groups that are identical, you can use EZ because it works across the board, but you can also use cis and trans nomenclature. So if something is cis, this is when they're on the same side. So cis means same. Let's keep it easy and just do a methyl group. So here, our higher priority groups are again the methyl group, and they are on the same side of the carbon. They're both up. They're both above the carbon-carbon double bond. So cis, this is cis. And if they are on, one is up and one is down, that would make it trans. They are opposite. The way I remember the difference between cis and trans, apart from the fact that we use those words a little bit more in like common use, and they have the same name, trans meaning opposite, transcontinental, going across the pond, so they're across from one another, and cis meaning same or together. I also, again, I know it's silly, but it helps me. What color am I? Green. But I also, you can draw the C for cis in that gap, which is how I've always remembered it as well. So cis, you can draw the C, so that makes it cis, whereas trans, they are opposite. But you only use cis and trans when you've got two identical groups. How are we doing for time? How are we doing? I'm not going to go through these in too much detail. I'm just going to allow you to have a go at these yourself. So label the following isomers as cis, trans, or EZ, or both, if possible. And again, you're going to get the answer sent out to you at the end when you filled in your survey. So hopefully, then you can have a look at how well you do. But I'm going to move on because I don't want to run out of time to do the final little bits. So, reactions of alkenes. Alkenes have a greater reactivity than alkanes. Why is that? Why do alkenes have a greater reactivity than alkanes? It's because of this high electron density double bond. It's because of the fact that alkenes have electron density above and below the plane of the bond. That means that the electron density is spread out and it's more accessible by nucleophiles or things that are, electrophiles, things that are attracted to areas of high electron density. So this is due to the high electron density of the carbon-carbon double bond. No, actually, I'm going to be much more specific than that. Of the pi bond, it's the pi bit of the double bond that's important. Sorry, I'm going to be specific because that is key. So, and again, I'm just going to scribble this out because it's technically the pi bond. The pi bond bit, so just, I would change that in your notes if you haven't already. The pi bond bit, just so we don't introduce a misconception. The pi bond has a lower bond enthalpy. So the pi bit of a double bond has a lower bond enthalpy than the sigma bit of a double bond. That means it requires less energy to break. Hence, the double bit of a double bond is easier or more reactive than a single bond. It's also, a pi bond also has a higher electron density. than a sigma bond. Hopefully, understandably, because you've got 4 pairs of electrons associated with a carbon-carbon double bond, so near to the pi, where the pi bond is, than you do in a sigma bond. If we think about the carbon-carbon bond strength, so carbon-carbon bond strength for a single carbon-carbon single bond is 347 kilojoules per mole. The double bit of a double bond, no, I lied. The whole of a carbon-carbon double bond requires 612 kilojoules per mole to break the whole of the double bond, but that's because it's made up of 347 approximately, which is the sigma bit, and 265, which is the pi bit, the double bit of the double bond. So actually the double bit of the double bond requires less energy to break than a sigma bond does. Alkenes are also attacked by electrophiles because of this high electron density. Electrophiles, which are electron pair acceptors, again, another definition you need to learn, and they're obviously attracted to the area of higher electron density, which is present, the area of higher electron density present in a carbon-carbon double bond. Some examples of electrophiles would be things like bromine, HBr, what else is going to accept H+, etc. Electron pair acceptors, you need to learn that definition as well, because you need to be able to recall it in an exam. That's what they're looking for. Okay, let's think about electrophilic addition then. Addition reactions are the bonding of 2 or more molecules to form a single product. That's why how we can work out if something is addition. You're combining 2 things to make one product, or more than 2 things to make one product. So for example, polymerization is technically an addition reaction. Addition polymerization with alkenes is an addition reaction. It's addition polymerization. You have actually got condensation polymerization, which produces another product, a second product, so that's obviously not addition. Okay, so for alkenes, this means that the pi part of the bond is broken to form a saturated organic molecule. For example, let's look at a general equation for an unknown alkene. Let's just do normal electrophilic addition. So let's add something across the double bond. We're going to end up with our species with X on one carbon and Y on the other. This is an example of electrophilic addition. We could actually, yes, okay, good. Yeah, no, I'm going to leave it like that, sorry. I was going to be more specific, but I'm not going to because we are low on time. So we have added X and Y across the double bond to form our product. Fabulous. If we wanted to be, let's be a little bit more specific here, with hydrogenation. What's hydrogenation? Hydrogenation. It's adding hydrogen. Hydrogenation is adding hydrogen across a carbon-carbon double bond. What are the reagents and conditions needed for hydrogenation? Well, obviously, we're going to need hydrogen, because you have to have the hydrogen you're adding, but also you need heat and a nickel catalyst. And that is a catalyst. So again, I'm going to just do a super quick example because we are low on time. And, I like talking too much. If we add hydrogen across ethene, we're going to end up with ethane. We have added hydrogen across the double bond. What about if we add something a little bit more interesting, so something that's not symmetrical, like water? Technically, water actually is a symmetrical molecule, but it doesn't split symmetrically, sorry, when we are adding it across a double bond. So what actually happens? What reagents and conditions are needed to add water across a double bond? Hopefully we know. If not, get it on your synthesis map and learn it. So we need high pressure, high temperature. I know it's not that high a temperature, but it's a decent high temperature. You need heat. And an acid, for example, H3PO4 or H2SO4, something like that. Excuse me. And again, I'm just going to keep it really simple because we're running out of time. Let's take ethane, and you're going to need your water, obviously. Otherwise, where are you going to, how are you going to add water across? And this time, water splits into a hydrogen on one side and an OH minus on the an OH on the other. So you end up with, in this case, an alcohol. We add the hydrogen on one side of the bond and OH on the other. In this case, we've got a symmetrical alkene. So we're going to produce, it's easy to work out what the product is going to be. We will, in a second, think about what happens when we have unsymmetrical alkenes. That's what I want to spend a little bit longer on. What about if we add a halogen, for example, so X2, so for example, bromine, Br2, chlorine, Cl2, etc. What happens? All we need to do is add the halogen itself. So we don't have any other conditions needed to add. Let's add chlorine across our double bond. And please, when you're doing it, hopefully you'll have a little bit more time. Try and keep your drawings a little bit neater than mine. Mine are not neat enough, really, because I'm trying to write quickly and think at the same time. Sorry, I think and talk at the same time. So, no, actually, okay. Apologies. I'm just going to give myself a little bit more space, and we're going to compare it to the next slide. So I will do it a little bit better than this. We'll think a little bit about the mechanism here. So what's going to happen when you have got, I did do chlorine, didn't I? Oh, I'm going to do bromine, because that's the more common one that you're expected to do. It's not the only one, but it is more common. So I might as well do it, and then you've seen it. So what happens when you've got, for example, bromine or a halogen that approaches a double bond, which is an area of high electron density? You've got an area of high electron density. That's lots of negative charge around that double bond. What's going to happen to the bromine? It's going to polarize that bromine bond. It's going to induce a dipole. Technically, that dipole could happen instantaneously. It could have been an instantaneous dipole that formed, but actually it's much more likely that it's going to be induced, because one of the bromines is going to be slightly closer to the double bond than the other, and that's going to repel electrons away from that bromine towards the other bromine. So you're going to get an induced dipole. Induced dipole. Hopefully I haven't got in the way of myself in a second. Again, now, how we're thinking about how these two things are interacting. We've now got a charge and we've got an area of high electron density. So the electrons are going to be attracted to the positive thing, and that's going to cause the electrons in that bond to move across to belong solely to the single bromine. That means we're going to end up with our intermediate species. Now, suddenly I've got a carbon with only 3 bonds. If a carbon has only got 3 bonds, it therefore is missing possession of an electron. That means it will have a full-on positive charge, must have a full-on positive charge. I haven't given it enough energy to exist on its own, and there is a deficit of an electron because that carbon is missing an electron. So it will have a full-on positive charge, and we also have a bromine over here, which has got a full-on negative charge because it gained possession of both the electrons in the bond when it only owned one of them. It had only one of them that was associated with it. Now what happens? We've got a positive and a negative. The negative electrons are going to be attracted to the positive charge. So they're going to move up. I've slightly got in my way there, and I should really point it at the carbon if I'm being correct here. Let's go straight at the carbon. There we go. And then we have got our dihalogenoalkane. Again, this is with a symmetrical alkene. So the carbocation intermediate that's formed in the middle, this is a carbocation. I won't draw that arrow because that is confusing. That is my carbocation species. If the bromine, I draw the bromine on the other carbon, it would have made a difference. The carbocation would have been identical. I just would have been drawing it from the back instead of from the front or whatever. They are identical. It doesn't matter because my alkene is symmetrical. Those carbons are identical, and therefore it doesn't matter which one the first bromine goes on. The second one is gonna, it will always produce the same product, sorry. How can I test for the present, oh, sorry, no, let me rephrase that. This reaction is how we test for alkenes. Sorry, I have written my induced, I thought I might have done, let's get that out of the way. Induced dipole. So bromine solution is used to test for unsaturated compounds, i.e. alkenes, because alkenes decolorize the brown solution. So it goes from orange to colorless. Oh, not orange, from brown to colorless. I think actually you can say orange. Orange to colorless if there is an alkene present. Because bromine is added across the double bond, that takes the brown/orange bromine out of solution, leaving us with a colorless solution. Okay. If we've got a hydrogen halide, it's the same as we've done before. I'm going to speed through it ever so slightly because I don't want to run over too much. So hydrogen halide, that means we've got a hydrogen and a halogen bonded to one another, so HX. If you have got a hydrogen halide, we have already got the dipole present. So it's the same as it was previously, it's just we already have a dipole. So you've already got the partial positive charge because a halogen is going to be much more electronegative than a hydrogen. It's going to attract a pair of electrons in that bond. So you've got your partial negative charge on the bromine, partial positive charge on the hydrogen. That means you can get the attack of the double bond immediately. You don't need to induce or wait for an instantaneous dipole to appear because it's a permanent dipole. I'll write that in a second. What am I doing? So then we end up with, now we add the hydrogen first because that's the thing with the positive charge. That's what was attracted or attractive to the high electron density in the bond. Again, though, we've now got one carbon which doesn't have all of its electrons that it should have around it. That means it's deficient. So it will have a full positive charge, but we have got a little bromine that has got a full negative charge. How are they going to interact? Funnily enough, you get the attack of the electrons towards the thing that they're attracted to, the positive. That's what causes the reaction, and you end up with the addition of the hydrogen halide across the bond. Here, let me just make sure I've written it in. We have got a permanent dipole though. Okay. Just as an aside, hydrogen halides tend to be gaseous under standard conditions, so they tend to be bubbled through the reaction mixture. So if you're talking about practicals, or if there's a practical question, you would talk about bubbling the hydrogen halide through. Okay. Now, I kind of wanted to have 10 minutes to do this, but never mind, we will have 5. We're going to think about asymmetric addition, or addition to unsymmetric alkenes. So when the alkene is asymmetric, it means the carbons are no longer identical. They've got different environments. If they've got different environments, they will behave slightly differently. This therefore means we can get 2 possible products formed. So if we have an unsymmetrical alkene, such as propene, and we add HBr to it, you've got to also be adding something that's asymmetric as well, of course, because if I added bromine, it wouldn't matter which way around the bromines went, they're identical. So HBr, so the hydrogen bromide, so that I've got two different atoms, so the products are different. You can see the products are different because here the bromine has been added to the central carbon, but on the right-hand molecule it's been added to the right-hand carbon. So those two molecules are different. When you do this in a laboratory, you'll find you have a mixture of products, but one will be in majority. One will form most of the product, and then there will be some that is in the minority. And which is which comes under Markovnikov's rule, which is spelt differently in all the different exam boards, which is great fun. But oops, we've spelt it like this. So this can be explained using Markovnikov's rule. What is Markovnikov's rule? Can we remember? How do we determine which is going to be in majority and which is going to be in minority? When you think about it, you've got to think about the process by which they get there, the reaction mechanism that takes them from this reactant to the product. Let's think about it here. In each case, you're going to get the attack of our electrophile, which has got its permanent dipole on it. Now, you could get attack via one carbon, so where one of the carbons bonds to the hydrogen, or you could get attack where the other carbon bonds to that hydrogen. That's going to form a different intermediate. That's going to form a different carbocation, because if we attack via the, and I'm going to make sure I get it the right way, the green route, let's go via the green route, we end up with a carbocation where the hydrogen has attached itself to the end carbon. So we end up with a carbocation where the charge is on the central carbon. That central carbon has got two alkyl groups attached to it. That makes it a secondary carbocation. If it's a secondary carbocation, it means it's got two groups attached to it. Both of those groups can give electron density to the carbocation. If it goes by the orangey route, the hydrogen attaches itself to the middle carbon, then the carbocation formed is on the end. If it's on the end of a chain, it's only got one alkyl group attached to it. It is a primary carbocation. Which is more stable, secondary or primary carbocations? Which are more stable and therefore which are more likely to form? If they're more stable, they're going to be more likely to form. Which one? Primary or secondary? It's going to be secondary because it's got two alkyl groups to stabilize that carbocation and not just one. Secondary, primary. Okay, when alkenes undergo electrophilic addition, an unstable carbocation intermediate is formed. Markovnikov's rule is explained by considering the most stable carbocation that can be formed. Alkyl groups, so carbon-based groups, are electron donating. That means because carbon is not very electronegative, it doesn't hog electrons. So if something is requiring electron density, it allows the electron density to be stolen from it, to be given to it. Alkyl groups are electron donating. The other phrases you might see are that they have a positive inductive effect, as in they allow electron density to be inducted away from them. Or you might see people saying that alkyl groups help to spread out the charge. Again, it differs slightly for what they will accept for different exam boards. So just double check for your specific exam board. Most of the time they will accept all of the definitions or all of the descriptions. But do just make sure that you're using the one that your exam board would prefer you to use, just so that you know you're going to get all the marks. Alkyl groups are electron donating. They stabilize this positive charge by spreading it out, by cancelling it out, or however you want to think about it. They stabilize this positive charge. If the positive charge is stabilized, that carbocation intermediate is more likely to be formed. Therefore, that is going to be the major product in this case. So this is going to form the major product. The more stable carbocation is going to form the major product, and the less stable carbocation will form the minor product.